Let us now look at the finite state machine implementation for the instruction load A using immediate addressing. The number one thing that you need to think about when you do an instruction is what the instruction is doing. When I say load A, it means information will be taken out of memory and put into a CPU register. The register in this case is A. When I say immediate, that means how do you treat the operand for that instruction? Immediate means the operand is the data. So if I write an instruction like this, LDA immediate, and I said AA, when I am done with that instruction, what I should see is the value AA, hex AA, located in register A. I named them all AA to make it obvious that A was updated. That's what you're trying to do at the end of this instruction. I put this in memory. Since this is the first instruction I'm going to implement, I'm going to put this guy in memory like this. I'm going to put it into memory starting at 0, and it will take 2 bytes, 2 locations of memory. The first one will be called LDA immediate. That's a mnemonic that we set up as a constant to represent 8-6. The operand will be located in memory right after it, and this represents the instruction. When I hit reset, what is going to happen is program counter is going to point to 0. And that is where you will fetch the opcode of the first instruction. This state diagram right here gives you the functionality that you will do. It is going to take 3 states to fetch that opcode. It is going to take 1 to give yourself enough time to decode it, and then once you know what the instruction is, it will take another 3 states to execute load A immediate. When these 3 states execute down here, what you're going to do is go out to memory, grab the operand, which is the data you want, and put it into A. After you are done with this, at this moment in time, register A will equal AA. You will then return to the top, and you will start over to get the next instruction. The idea here is this. These states have been provided to you by me in order to walk you through how to execute a few of these instructions. Right now, at this point, you should have everything coded in your computer except for the finite state machine. You should have the data path, all the registers, all the multiplexers. You should have the memory system coded, the ROM, the read-write. You should have the data path all done, but not the control unit. You should have the memory system done, and in your ROM, you should have, at least at address 0, programmed up with load A immediate and AA. You're then going to simulate this and watch these instructions get executed. You should know how to take a state diagram and code it as a finite state machine using the 3-process model that we've covered so many times. Let us look at the VHDL for that, though, and let's look at it in Model Sim itself. So I'm going to leave that state machine over there, and I want to go up here, and I'm going to look at the actual VHDL for the finite state machine. It exists in the control unit. The control unit is a monster. It is where all of this functionality for the finite state machine will reside. When I look at this, I need to have the constant mnemonic table, which has the op codes for all these mnemonics. In this computer, you have to have it in 2 places. You have to have these codes in the memory system ROM and also in the control unit. It's a real cheap way to do it. It's not a global variable. It's not a global constant. I did them as local constants just to make it cheap. But they're sitting in there. There are 4 things that you do when you create the finite state machine in VHDL. 3 processes and also the state definition. The way that you do the states is you create a new type called state type, and then you give it every value that you want. If you look at this, I am going to create state names for everything in this state diagram. So when I want to have a state called sfetch0, sfetch1, sfetch2, I need to go over here and I need to define them as s underscore fetch0, s underscore fetch1, s underscore fetch2. If I want a decode state, I'm going to go s underscore decode 3. For this particular instruction, I'm going to have s underscore LDA underscore IMM underscore 4 underscore 5 underscore 6. Note that I put an S at the beginning of each of these to know that it's obviously a state. So when I look at my simulation, I know that it's a state when I look at current state. I put the name of what I'm trying to do, fetch, decode, or the particular instruction, as part of the state name. That's to make it readable. That's the power of Vhdl. You can look at your simulation and know exactly what you're doing. Then what I chose to do is to put an underscore number after this. So I can actually, if it executes correctly, I should always see it go 0, 1, 2, 3, 4, 5, 6. In this one, this is our first instruction. But think about when we do our next instruction. You'll still see 0, 1, 2, 3. Then you should see a 4, 5, 6, 7 for the next instruction. Okay, so it's just multiple ways to know what's happening. When I do that, I now can create 3 processes that use these state names. When I scroll through my VHDL, I am going to add states every time I implement a new instruction. And look at them go, look at them go. They go forever, and you add them one by one. I then say to you, create the state memory. The state memory does nothing more than update current state with next state on the rising edge of every clock. So you enter a process which is called state memory, if you want to name it. The clock and reset are the inputs to this process sensitivity list. It's nothing more than D flip-flops. You say, if I get a reset, where do I go? Critical that you go to fetch 0, because that's where you want your computer to go once you start executing your program. That's the reset. You could call it the reset vector. That's where we're going to go execute code. You also better make sure that when you go to that state, okay, it's going to go fetch at the location of memory that corresponds to the first opcode you want to execute. I then say, otherwise, if you get a rising edge of a clock, update current state with next state. Piece of cake. The second process is going to be your next state logic. This computer is actually very linear in the way that it executes states. It really, for this instruction, only has one state where it may take another path. Okay? That's the decode. Since this is our first instruction, it's not that big of a deal, but look at the way it's going to execute. If I'm in fetch 0, go to fetch 1. If I'm in fetch 1, go to fetch 2. If I'm in fetch 2, go to fetch 3. I just code up the next state logic and I assign to next state. Is next state combinational logic or sequential logic? Combinational logic. That means you need to have everything in the sensitivity list that could trigger this process. That is absolutely current state, but it's also the instruction register, that's an input, and the CCR result, which is an input, but you don't need it yet. How would you know that those are inputs to the finite state machine? You come over here and you look at the drawing and you see that IR comes in, CCR result comes in, and the current state, of course, is embedded. That's how you knew what it was. Okay, look at what I do. Fetch 1, fetch 2, fetch decode 3. And then I finally make a decision. I finally say, if I'm in decode 3, if the instruction register says load A immediate, go down and execute these particular paths. But this is where you put the decision on what instruction you're actually going to execute. It is one big if-then statement. And that's what you do. When you decode, you look at the instruction register and say, oh, I got LDA immediate. That means go to these paths in my state machine. Oh, I got something else? I'm going to go somewhere else and execute some paths. So this is the only if-then statement in this particular next state logic. Look at what happens. It grows pretty substantially, because once you actually make the decision of what instruction you're executing, then you go down and you have to then create the next state logic for the states that you're doing. It's not just one more state, right? It's load A immediate 4, 5, 6, and then back to fetch. So the way that you do that is I put these next state decisions in here, and I say if current state is LDA immediate 4, go to 5. If it's 5, go to 6. If it's immediate 5 or immediate 6, go to fetch 0. Note that you don't have to code every instruction at the beginning. Code one instruction at a time. Make sure that it can execute. Okay? Now, that's the next state logic. Here comes the big dog, though, the output logic. This machine only depends on the current state. It is a more machine, more type machine. The output logic only depends on current state. At every single state in this state diagram, what I do is I list only the signals that will change. That doesn't mean you don't drive every single signal, because as a control unit, you definitely need to drive all these signals. You got to drive IR load. You got to drive MAR load. You got to drive PC load, PC inc, A load, B load, ALU select, bus 2 select. You got to drive them all. What I do is I say, I'm only going to list the ones that actually are changing in this situation, the ones you care about. You know what I do with all the other ones? I just drive them to zeros. So when I start my VHDL, I list every single output. And I say, for the first state, fetch 0, I set them all to zeros. Then I go over to the state diagram and see which ones am I actually changing. In this situation, only 3 will actually be updated. Bus 1 select, bus 2 select, and MAR load. I go over to here, and those are the ones that I actually change. Bus 1 select and bus 2 select are multiplexer controls. You got to know what code is going to choose what in the multiplexer. You know what I did to make it easy? I just went ahead and put a comment behind it, and that allows me to quickly look at my VHDL and know, oh, if I do 0, 0, that means I want to select the program counter as what is going to go out to bus 1. If I select 0, 1, that's going to be A. If I do 1, 0, that's B. This little comment right here is my best friend, because I can look at it and immediately know what to do. Now, those output signals, we don't even know if they work. You don't even have to know how this instruction works if you just code it directly from the state diagram. When you do it, you will absolutely learn how it works, but that's why I give this to you the first time. You could actually get this whole thing working without even understanding what's going on, because I give you this. Look at sfetch1 and let's see if we can figure out what its output logic should be. I have to have these assignments for every state. That's why the output logic process is monstrous, because I put them in a column. Some people put them in rows, whatever you want. I'm a column guy myself, no reason. So I come down here, and that's for sfetch0. I'm going to do the exact same thing. When I'm in sfetch1, I will copy and paste all of my output signals, and I will then update them. I put them all to 0, and then I think about what am I trying to do. In sfetch1, I'm going to increment the program counter, so I go ahead and increment it. Everybody else goes to 0. Okay, could we keep this going? What about sfetch2? I look at this sfetch2 state diagram. I copy all of my output assignments. I set them all back to 0, and then I think about it. I say bus 2 select gets from memory, and then IR load. So I come in my table, look at what I did. IR load is a 1, whatever. I come down to bus 2 select from memory. Look at how I can code this directly from the state diagram without even knowing what I'm doing. Who knew what to do? It's the state diagram. This was drawn by somebody who knew how to move the signals back and forth. Okay? This is then how you go with these guys. Look at decode. It had outputs. You know what? So did load A immediate. It had load A immediate 4, 5, 6. Then guess what? You add in more instructions. How about direct? A direct? Why not? Store A direct? Why not? Load B immediate? Oh my goodness, in the morning. We are going and going and going and going. I got a lot of VHDL here. You going to type it? Negative. You're going to type it once, and then you're going to copy and paste. But it can be quite intimidating and overwhelming if you don't comment it. So what I do is I try to make these comment basically dividers. That's why you don't do it all at once. Don't paste in every output logic for every state that you think is going to be in the computer. Get one instruction working, then move to the next one. That's the way you can debug and move on to the next. Okay, this feels phenomenal. I know how to code the VHDL. Now let's just go through why we are actually moving these states the way that I am moving them. So this now becomes my program, and I want to look at where things are going in my actual data path. Why did I assert these signals the way that I did? If I look at this state diagram, I am trying to go out. Let's put the state diagram over here so I can see my memory. Okay? And I'll put the data path right here, and I say to you, go. Go means reset. Boom. It is going to try to go out. What am I doing here? I want to put this guy right here. I want to put my memory system right here. I've got 0 and 1, and I've got 8, 6, and I've got A, A. Okay? So now what I'm going to do, even better, even better. When I said go, that meant program counter gets a 0, and I want to start executing. I change my buses, bus 1 select and bus 2 select, in order to get 0, 0 through this multiplexer onto bus 1, over through this multiplexer onto bus 2, and then I did a mar load. The next state I see that mar got 0. Then I take a minute and I increment the program counter in the next state, and that takes that to 1. Why did I do that? I did it because I wanted the program counter to point to the next location in memory. I now am waiting for the memory to produce the opcode. This address went out to the memory system. Here comes 86. 86 is coming out, and it's going to come in from memory. So 86 is hanging out down here. What do I need to do? 86 comes in the fetch 2 state. I need to change this multiplexer to allow 86 to come onto here. So what I do here is this guy comes up, comes through this multiplexer, and comes into here. When I say I need to change it so that comes in there, I do it by changing bus 2 select to equal 86 on the next edge of clock. How's that feel? That felt pretty good. When you look at it in simulation, it's critical to think about when these things take place. When I think about when a load makes the register update, it only updates on the next edge of clock. So if I look at this, I go fetch 0, it produces 0 on the program counter, it is loaded into mar on the next edge of clock. Then I increment the program counter, it is incremented on the next edge of clock. I then bring in I bring in the opcode and I do IR load. Look at when it actually pops into the instruction register. So I know this worked by looking at this guy right here. I got 86 right there. The program counter is pointing to 0, 1, which is where I want it, and I'm good to go. I then did my decode, and what is next is I'm ready to say, let's go get the information that's the operand, bring it over, and I know by the instruction design, it is the data to load into A. So think about the states I need to do. I'm going to do almost exactly what I just did. I need to take the program counter, and I need to get it into MAR. So I'm going to, again, come along and say, I need to take this guy right here, program counter, and change bus 1 select to be the program counter. Then the program counter comes over to here. I need to change bus 2 select to choose bus 1. And then I'm going to do a mar load. Once I get done with that, the mar will actually be equal to 1. And then I'm going to increment the program counter so that it's pointing to the next location in memory. And I will then wait for the memory system to respond to my address. I do program counter inc in a different state because I need to wait anyway, so I just separate it out and put it there. Here comes AA. It comes through, it comes back from memory, and it is now going to be on the from memory bus, and I need to now go get it. So I'm going to take this state right here, SLDA IMM6, and I'm going to change this multiplexer to allow from memory to drive bus 2. Here's AA. And now this is where you got to think, what is the purpose of this instruction? It's to put that operand into register A. So who do I do? What load do I do? Boom. A load. A is now equal to AA. Guess what? I'm done with my instruction. A has the value that I wanted. It has the operand. And more importantly, the program counter is pointing at the next location in memory. I return to my fetch, and I'm ready to do the next instruction. And that is load A immediate.